We are here today to discuss about logic gates. The first question is, what is a logic gate? If we see the word logic gate, it is comprising of logic and gate. So there must be some gate which follows some logic. So if we construct the electronic circuit, so there must be some signals, electronic signals, which are coming inside through the gate and appearing at the output. So we have some input, some output, and also as a gate we should have some digital circuit. So there must be a logical relationship between output and inputs. So a logic gate can be defined as a digital circuit with a logical relationship between inputs and outputs. That is, input should follow, the input signal should follow some condition to appear at the output. So such type of gate is known as the logic gate. Now, what are the logic systems? So how do they manage? So here there are two types: the DC or level logic system, or the dynamic or the pulse logic system. So again we can categorize DC or level logic system in two parts, as a positive DC or level logic system and a negative DC or level logic system. So in DC system, what we take, we have a signals in DC form, in the voltages form. So it might be, and we recognize the states of voltages by the two different voltage levels. So we have a 0 state and 1 state. The 0 state is recognized by the lower voltage, and the 1 state is recognized by the higher voltage in a positive DC logic system. So in general, V1 state, the high state is recognized by 4 volt, which may vary from 3 to 5 depending upon the circuits or the devices we are using. In a similar way, 0 state is recognized as 0.2 volt, which again may vary from 0 to 0.5 volts, sometimes 0.7, 0.8 volts also. In negative logic system, the higher state is assigned by the lower voltage, and the lower state is assigned by the higher voltage. That is, we can say that 0 state or the low state is assigned by 4 volt or from 3 to 5, which may vary from 3 to 5 volts, and similarly the higher state is by 0 volt or up to 0.7 volt. In dynamic or pulse logic system, again we can divide it into two parts: positive pulse logic system and negative pulse logic system. Here, instead of giving a DC level voltage, constant voltage level recognized by 0 state or 1 state, we give pulses to as a input, and we receive pulses as a output. In positive pulse logic system, we give a positive pulse, and 0 state is recognized by 0 volt, and higher state, 1 state, is recognized as in general by 5 volt. In negative pulse logic system, we apply a negative signal, negative voltage signal, which is recognized, of which the 1 state is recognized by -5 volt, and the 0 state is recognized as 0 volt. So this is the logic system. Now if we recollect all the information, then positive DC logic system, further discussion, we will assume that V1 state, the higher state, as a 5 volt, and the lower state, that is 0 state, as a 0 volt. And in negative DC logic system, we have 1 state as a higher state as a 0 volt, and the lower state as a 5 volt. So in our next discussion, we will assume only the positive DC logic system. So far we have seen that in digital systems we can give either 0 state or 1 state. We cannot give a state in between them. So we can say that digital system functions in binary manner, means it assumes either low state or high state, that is either 0 or 1. We can say that it assumes only 0 bit or the 1 bit. So And the devices like diode or the transistors which we are using, they are working either in the cutoff region or in the saturation region, but not in active region, which we will see in further discussion. So before going to the different gates, it would be beneficial if we recapitulate our information of the PN junction diode and a little bit about the transistor. So we will discuss first to the IV characteristics of PN junction diode. So we will see how the PN junction is connected in forward bias condition. Here we see that this is the PN junction, P type and N type, and this is the junction. And in forward bias, the battery, the positive terminal of the battery is connected to the P terminal of the diode, and the negative terminal of the battery is connected to the N terminal of the battery. And this is the voltage which we measure across the diode, and this is the current which we can measure, and this is in milliampere range when it is in forward bias condition. And in reverse bias condition, we see that the positive terminal of the battery is connected to the N terminal of the PN junction diode, and the negative terminal of the battery is connected to the P terminal of the diode, PN junction diode. And this is the voltmeter which is connected across the diode, and this is now in reverse bias condition, the current is very small, reverse saturation current, which is in microampere when we use a germanium PN junction diode, and it is in nanoampere if we use a silicon PN junction diode. Now this is the IV characteristics of a PN junction diode. In this side voltage is positive, in this side current is positive, in this side the voltage is negative and current in this direction. So we see that if we increase in forward bias condition, as we increase voltage, current does not change very much. After a particular voltage, which is V knee, also known as the knee voltage, or it is also known as the cut-in voltage or threshold voltage. If we increase voltage beyond V knee or V cut-in, then current increases very sharply. And in the reverse bias condition, we see we increase the voltage in reverse direction, and we measure current in microampere or nanoampere depending upon the which kind of diode we have taken, which kind of materials we have used in making diodes. So we see that the current is very small, few microampere or few nanoampere only. So we can say if the input voltage is less than V gamma, which is V knee or V threshold voltage, a cut-in voltage, diode will not work. It is in off condition, and at output we get almost the supply voltage, that is V out is high. Now if V in, which is the input voltage, is greater than V gamma, here we can see the knee voltage is greater than V knee, then current is very high and it is in on condition, and V knee for germanium crystal is 0.2 volt and V knee or V gamma for silicon is 0.6 volt. So if voltage is greater than 0.3 volt, it gets in saturation. So we have a huge current, and the voltage drop will be only 0.2 or 0.3 volt if the semiconductor or PN junction is made of germanium crystal. And if it is made of silicon, then the voltage drop across the that PN junction will be 0.6 or 0.7 volt. So that is the by our definition for positive DC level logic circuit, it is a low state. So now we will keep these things in mind for our further discussion. It would be also beneficial if we discuss a little bit about the transistor IC versus VBE. VBE is the voltage between base to emitter junction of a transistor. So this is a basically NPN transistor. VBB and VCC are the bias voltages at base and collector respectively, and this is the IC current which is flowing through the collector. IB is going into the base, and this V output is taken at the collector junction. RL is the load resistance. So this is the characteristic curve. Means we have plotted IC and VBE on x-axis and IC on the y-axis. Here the axes are not scaled. So here again we see that if we increase VBE, that is the voltage between base to emitter. So if we increase, then we find a very small current IC through the collector, and when VBE is greater than some particular value, again we will say V gamma or cut-in voltage, again current increases very sharply. So we we have taken V out at the collector junction. So if we apply Kirchhoff law here in this loop, in the collector emitter loop, then we can say minus VCC plus IC into RL plus VO will be equal to 0, or VO will be equal to VCC minus IC into RL. So we see here when voltage VBE is greater than V gamma, we have a huge current here, and IC will be very high. So this whole quantity will be very low and VO will be low. So we see here VBE, if VBE is less than V gamma, this Q, the transistor, will be off, and if it is off, then IC will be approximately equal to 0, which it may be in microampere reverse saturation current. So VO will almost be equal to VCC. So output will be high, means in terms of, if we talk in terms of the digital system, that is in high and low. And when VBE is greater than V gamma, this transistor Q will be on. Here we can see if it is greater than V gamma, so there will be a huge current through the collector and Q will be on, and since IC is very high, so VCC minus IC into RC will be very low, so output will be low. So we have to keep again these things in mind when we discuss the NOT gate and other gates. Now we will start logic gates. So there are many types of gates: OR gate, like AND gate, NOT gate, NOR gate, NAND gate, exclusive OR or XOR gate, exclusive NOR or XNOR gate. So here OR gate, AND gate and NOT gate, they are known as the basic gates, and here the other last 4 gates, they are known as the combination of the basic gates, because we can realize them using these 3 gates. And NOR gate and NAND gate, they are very important. They are known as the universal gates because we can realize all other gates using either only NOR gate or only NAND gates. Now we will study one by one and we will discuss. So we have OR gate. So first we will realize it, we will discuss it using switches. Here let us consider this circuit. We have a voltage supply voltage, which is connected to a bulb through 3 switches S1, S2 and S3. We will recognize the states as follows. When S1 is open, we will recognize it as a 0 state. We will assign it as a 0 state. Any of the switch is open, we will recognize or assign it as a 0 state. When it is closed, then we assign it as a 1 state. Similarly, when bulb is on, when bulb glows, then we will recognize it as 1 state, and it does not glow, then we will recognize it as a 0 state. So now we can see from here, from this circuit, for example, if suppose S1 is on, means S1 is closed, but other 2 switches S2 and S3 are not closed, then the current will flow through the S1 to the bulb, and this bulb will be on. This bulb will glow. If any of the switch is on, for example, if S1 and S2 is closed and S3 is not closed, it is open, then the current will flow and this bulb will be glowing. So we can see that if any of the switch is closed, then we have a one state, or we have a on state of the bulb. So the bulb glows if any of the switches is on. So now we will define OR gate. What is OR gate? An OR gate has two or more inputs and a single output. If we recognize S1, S2, S3 as inputs and Y, the glowing of bulb, is as an output, so the output is high, that is in one state, if one or more inputs are high. Means if any of the inputs is high, the output will be high, and output will be low if all the inputs, means here we can see that the bulb will not glow if all the switches are open, and this is the only condition when this bulb will not glow. So we can say that we will be getting zero state if all the inputs are zero. Now we will realize OR gate using diodes. Now consider this circuit. We have three diodes, D1, D2 and D3. They are connected. A, B and C are the inputs to the P terminal of these diodes, and the N terminals are connected together through this resistance R, and output has taken through the across this resistance R. So now and this is the inputs, one state and zero state. We have taken a battery of 5 volt. One state is recognized by the 5 volt and zero state is recognized by the 0 volt. So if A is 1, for example, if we consider all the switches are connected to zero state, means all the inputs are 0, A, B, C are 0, then what will happen? This D1, D2 and D3, they will be in off condition, no current will be flowing through the circuit, and we will not get any voltage drop across this resistance R, and then output will be low. Now if we consider A as 1 and B and C as 0, if A is 1, then this D1 will be in forward bias condition, and D2 and D3 they will be in reverse bias condition. So D1 will conduct, but D2 and D3 they will not be conducting. So if D1 will conduct, then current will flow through this resistance R going to the ground. So there will be a voltage drop IR across this resistance, and we will be getting output as high. Since this is 5 volt, so the voltage drop across, as we have discussed already, the voltage drop across D1 will be around 0.2 volt if it is made of germanium, and it will be around 0.6, 0.7 volt if it is made of silicon. So the rest of the voltage drop will be here at across the resistance R. So here we will be getting around 4.3 or 4.7 volts depending which kind of diodes we have taken. So this will be high. So again we can show that if any two of D1 and D1, D2 and D3 are high and one is low, even then this two of them will be conducting and output will be high. If all the three diodes D1, D2 and D3 are connected to one state, then this all will be conducting and we will be getting current across resistance R, and output will be high. So we can say output Y will be equal to 1 if any of the inputs is high. Means at least one input should be in high state to get output high. So again we can say when the output will be low, it will be low only when all the diodes are connected to zero state. So this is the symbol for OR gate. These are the A, B, C indicating inputs, and output Y indicates output of the OR gate. We may take any number of inputs, but at least two inputs. There should be two inputs in a OR gate. So truth table of OR gate. Truth table means the logical relation between inputs and outputs. So if we have to verify any gate, then we have to verify the truth table of that gate. So we can see these are the various possible inputs. If we take 3 input OR gate A, B, C, so it may take, there will be 8 possible states: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So 1 stands for 5 volt and 0 stands for 0 volt. So if we can see from here that output is in 0 state only and only when all the inputs are in 0 state, and output is in 1 state if any of the input is in 1 state. So now we will discuss the Boolean identities. Boolean identities, in Boolean identities we have some logical inputs like A, B, C, whatever, and we see the relationship between logical inputs following the OR gate. So now we may add anytime, any way, A plus B plus C. We may add A plus B first and then to C, or we may add B and C first and then to A. So A plus B plus C is equal to A plus B plus C is equal to A plus B plus C. It follows the commutative rule, A plus B is equal to B plus A. Here we should take care that A and B can assume either 0 or 1, not in between. It can assume either 0 state or 1 state. A plus A is equal to A. This is very much obvious. If we take A is equal to 0, then 0 plus 0 will be equal to 0. If we take A is equal to 1, then 1 plus 1 will be equal to 1. 1 plus 1 means the 2 inputs is in 1 state, then output will be in 1 state. This plus indicates the OR operation. So A plus 1 is equal to 1. A is the one input, and if the second input is in 1 state, then we can means the output will be independent of the first input. So whatever be the value of A, output will always be 1. A plus 0 will be equal to A. If the second input is pre-assigned to 0 value, then output will be decided by the first input. If it is 1, then 1 plus 0 will be 1, and if it is 0, then 0 plus 0 will be 0. So A plus 0 is equal to. So this was all about the OR gate. Now we will discuss the AND gate. So in AND gate, again we will discuss first by using switches. So here, now consider this circuit. Again we have a battery connected by a bulb, which we say that this is the output, connected through the 3 switches S1, S2, S3. Again we will say that if switches are open, it is recognized as a 0 state. If switches are closed, it is recognized as a 1 state. Similarly, if bulb is glowing, then it gives 1 state, and if bulb doesn't glow, it means that it is in 0 state. So if we see, very easily we can recognize that this bulb will glow if all the switches S1, S2 and S3 are in closed state. That is, if they all are in 1 state. If any of S1, S2 and S3 is open, that is in 0 state, this bulb will not glow because current will not reach to this bulb, as the circuit will be discontinued. So here we see that the bulb will glow when all the inputs S1, S2, S3 is in 1 state, otherwise it will not glow. So we can simply see the bulb glows if all the switches are on. So now we define the AND gate. Again, it has 2 or more inputs. It's a logical circuit with 2 or more inputs. The output is high, that is in 1 state, if and only if. Here this is very important terminology in mathematics. If and only if all the inputs assume the 1 state. So this is the only condition when we will be getting high state at the output. So output will be high if all the inputs are high. If any of the inputs is low, the output will be low. So now we again realize AND gate using diodes. Here let us consider this circuit now. Again we have 3 diodes, D1, D2, D3. A, B, C are the inputs. In this case, the diodes are connected in reverse bias way, where the inputs are provided are implemented at the N terminal of these diodes. A is implemented at the N terminal of D1, B is implemented at N terminal of D2, and similarly C is implemented at N terminal of D3. The P terminal, it is connected, we have taken output at the P terminals and between the ground, and this resistance R is connected through this positive voltage 5 volt. And here we have given the states by giving 6 volt battery. One state is plus 6 volt and 0 state by 0 volt. We will see why we have given 6 volt, not 5 volt. So now if we assume that A, B and C, all three are in 0 state, so what will happen? So this D1, D2 and D3 all will be in forward bias condition, because 5 volt is applied at P terminal, and this A, B, C is since they are connected to 0 volt, so they will be in forward bias condition. So they will all be in conducting state, and since we have taken output at P terminal and the ground state and the ground, so we will be getting the voltage drop only 0.3 volt, which is the saturation voltage, 0.3 volt if it is germanium, and 0.7 volt if it is a silicon diode. Now, so the output will be in 0 state. If all the D1, D2, D3 are in 0 state, output will be in 0 state. Let us suppose that D1 is in 1 state and D2 and D3 both are in 0 state. So we have condition 1, 0, 0. So in this condition, this D1 will be conducting and there will be a current will be conducting, though D2 and D3 are not conducting. So the current will flow through D1 and the output will be again low, because we will be reading the voltage drop across the P terminal and N terminal of D1, and which will again be either 0.3 or 0.7 volts depending on germanium or silicon type of semiconductors we have used for making this D1, D2, D3. So now if we assume all D1, D2, D3 are in one state, so now if D1, D2, D3 are in one state, that is the N terminal is connected to 6 volt and P terminal is connected to 5 volt. This means that D1, D2, D3 they all will be in reverse bias condition. So no current will be flowing, and the current, if the current is flowing, that will be in micro or nano amperes. So no current will be flowing in principle through the D1, D2, D3, and whole voltage, this 5 volt, will appear at this point at the output. So output will be high. So we can see very easily that we will be getting output high if and only if all the D1, D2, D3 are connected to one state. If any of D1, D2, D3 is connected to 0 state, then at least that diode will be conducting and we will be getting low output at the output terminal, means the 0 state at the output terminal. Now why we have taken 6 volt here, not 5 volt? Suppose if we would have taken 5 volt here, then what happens, this and if we give all D1, D2, D3 as one state, so this is 5 volt and this is also 5 volt. So sometimes due to some electronic fluctuation, because only we need 0.2 volt if it is made of germanium to get to transfer this diode into the saturation state. So this is very low, and due to any electronic fluctuation, it can go to beyond 0.2 volt and voltage may go in saturation. So to keep ourselves, our electronic device to AND gate in safer side, we take 6 volt, means that is the higher voltage than 5 volt. Now, which as we have discussed, output Y will be 1 if all the inputs are high, that is if all the inputs are in one state. Now the symbol for the AND gate is like this. These A, B, C, we can take any number of inputs A, B, C, D, E, F, G, H, and but at least 2 we need. So we have A, B, C as a input and Y as a output. Now truth table of AND gate. Again we will discuss the truth table as we have already discussed in our previous slide, that A, B, C are the inputs and output is Y. So again, if all the A, B, C are 0, output will be 0. If any of the input is in 0 state, up to here we can see, here the C is 0, here only B is 0, here only A is 0. So if any of the input is in 0 state, output will be in 0 state. So output will be in one state only and only when all the inputs are in one state. So this is the truth table for the AND gate. Now we will define some Boolean identities which following the AND gates. Now we have already studied the OR gate, so there may be a combination of the Boolean expression for AND and OR gates. So here ABC, ABC means A and operation B and operation C. It may be equal to ABC or ABC. Similarly, AB is equal to BA. Means we can interchange the inputs. We can put A at first terminal, B on the second terminal, or the first terminal we can first give B and the second terminal we can give A. Again we have to take care that A and B, either they can assume 0 state or in 1 state. A into A means AA will be equal to A, which is very much clear. If A is 0, so 0 into 0 means 0 and operation 0 will be 0, 1 and operation 1 will be 1. A into 1, that is, if we have pre-assigned the second input by 1, then the output will be decided by the first input. If A is 0, then 0 into A will be A. We should not say actually into, but for our convenience we are saying it as a input. It is in fact the AND operation. So A into 1 will be A. If we say A is equal to 1, then 1 into 1 is equal to 1. If A is 0, then 0 into 1 will be equal to 0. Yes. Now if we assign the second terminal as a second terminal of a AND gate as a 0, then output will always be 0, whatever be the value of the first terminal. Now here we have a combination of operations, the AND operation, and this plus indicates the OR operation. If we have, this is in fact the distributive law. This follows the distributive law, that is A into B plus C is equal to A into B plus A into C. We can verify all these Boolean identities here and also which we have discussed in OR gate by just putting them on truth table, by taking the different values of A, B, C, and we can see we can find out A, B, C, we can find out first A, B and then multiply it by C. Means in the same way, means in this way we can verify all these Boolean identities just by going to the truth table. So this is all about the AND gate. Now we will discuss the NOT gate. Now the NOT gate using switches. Now let us consider this circuit again. Here we have a battery of voltage V which is connected to a bulb Y. We say that we recognize it as a output through a switch S. So we see if switch is open, that is S is 0 state, then the current will flow through the this bulb and this bulb will glow. So if S is 0, this bulb will glow, which we have recognized as a 1 state. So if S is 0, we have output as 1 state. Now if we say that switch is closed, if switch is closed, then this current will flow through resistance R, as we have already told that this R is very less in compared to this bulb. So the whole current will flow through this resistance R and no current, almost no current will flow through this bulb Y. So we will not be getting any output, means output will be 0, bulb will not glow. So if switch is on, that is switch is closed, that is switch in 1 state, input is in 1 state, output is in 0 state. So we get output as a complement of input. So this is a NOT gate. NOT gate means inverted, whatever you have input, that is inverted at the output. So now we say this is, we can say that this is the truth table for NOT gate. Here we have recognized S as a input and bulb, glowing of bulb and not glowing of bulb as a Y output. So if 0 state means switch is open, the bulb will glow, we have one state, and if we have one state, that is switch is closed, this is output will 0, that is bulb will be in off condition or bulb will, does not glow. So 0 corresponding to 0 we get 1, corresponding to 1 we get 0 at the output. So the output is inverted. So we can say that output is inverse of the input. So that's why it is also known as the inverter circuit or the simply NOT gate. The symbol for NOT gate is this. Here, unlike OR gate and AND gate, we have a single input and single output. So this bubbled, this circle at any means we will see later also, at any electronic device in digital system will invert the input. So this is the symbol for the NOT gate. Now again, as usual, NOT gate we will realize using a transistor. So this is a let us consider this circuit. Again we have a NPN transistor. This is a plus VCC supply for collector junction, collector emitter junction, and this plus 5 volt is again given to this terminal as 1, and this here we see that emitter terminal is grounded and this terminal is recognized as a 0 state. So now this A is input and we have taken output at the collector terminal. So we can connect A at this point, then this will assume 1 state, and if we put A here, it means connect to this point, then this will assume as a 0 state. So now you see, if A is in 1 state, then there will be a considerable current through base, and this transistor will be in on condition, as we have seen in our previous slides, that for IC versus VBE characteristics, that when VBE was greater than some cut-in voltage, this transistor was in on condition. So again the same principle, if A is connected to 1, this transistor Q will be in on condition, there will be a heavy current through this resistance RL, and since we are measuring voltage across this collector and ground, that is the emitter. So V output is again VCC minus IC into R. When this Q is in on condition, this will be a large quantity and we will be getting VO as low. So when A is in 1 state, this Q will be in on condition and output will be low. When A is in 0 state, we may have a condition that V is less than V gamma, this transistor Q will be in off condition, there will not be any current and the whole voltage will appear at this Y, because if IC will be equal to 0, then VO will be equal to VCC. So we can just draw the truth table for NOT gate. We have input A here and we recognize as action and output. If A is 0, as I told, that Q will be in off condition, output will be in 1 condition, means at output we will be getting 1. If input is in 1 condition, input is in 1 state, the output Q, this transistor Q will be in on condition and output will be 0 state. So now for the NOT gate we have also few Boolean identities. This line I will say as a bar or complement. So complement of complement is the input quantity itself. So if we have one input at the NOT gate and it is complemented 2 times, it is taken reverse 2 times, then we will be getting the original quantity. Now A bar plus A is equal to 1, because as I told that if means A can assume either 0 state or in 1 state. So this plus is the OR operation. if we have assumed A as a 1, then A bar will be equal to 0. So 0 plus 1 will be 1, or if we take A as a 0, then A bar will be 1. So 1 plus 0 is equal to 1. So this is very easy to understand and very easy to discuss. So A bar A is equal to 0. It is also very easy to understand. If we take A as 0 state, then A bar will be in 1 state. So 1 AND operation 0 will be equal to 0. Or if we take A as a 1, so 0 AND operation on A with 1, that will give again 0. So this is all about the basic gates we have so far discussed as a OR gate, AND gate and NOT gate. So these are the basic gates, because other gates like NAND gate, NOR gate, exclusive OR gate and exclusive NOR gate, we can realize by using these basic building blocks. So far we have studied the Boolean identities of NOT gate and other gates. In next session we will discuss the rest of the logic gates, which are XOR, XNOR, NAND and NOR, and we will realize the different gates. Thank you.